Okay, all right. So, yeah, we'll look at graphs of log functions, and we'll do the transformations. The transformations are all the same, regardless of what the function is, so that makes that a little bit easier to learn. So one of the key things that you learn in this section is when you do a log, you can only do a log of a positive number. Okay, so as we look at this, like if you do a logarithm of 2, you get an answer. If you do a logarithm of 10, you get an answer. You can't do a log of 0. You can't do a log of a negative number. What will happen on a calculator is, if you do a logarithm of any positive number, you're going to get an answer. Okay, if it turns out to be a decimal, then there's no way in the world you could do that problem in your head. If it turns out to be a nice whole number, like if I did the log of 100, that's 2, well, you could do that in your head because that just means 10 to the seconds equal to 100. If you do a log of 0, you're going to get an error. It's going to come out like this. It's going to say that there's some sort of an error on that. Now, in a more advanced class, there's a way to work around that, but we're not in a more advanced class. If I do a logarithm of a negative number, like if I do a logarithm of -2, for instance, you're going to get an error. So I'm going to talk about why you can't do a logarithm of 0 and negative numbers, okay? This thing right here also, you'll hear me kind of use this terminology. Whatever you're taking the log of, we call that the argument. That just means that's the expression we're taking a log of. All right, so let's go through and just kind of look at why this works the way it does. All right, now if you go to this example 1, let's work out A and B the way I already taught you how to do this. And I taught you to just set this equal to x, write it in exponential form. So that would really be 10 to the x equals 10. Okay, so what's x? 1. So the answer is 1. That's the same thing I just taught you guys. Okay, part B, same thing. We say log base 10 of 1 equals x. Write it in exponential form. You'd have 10 to the x equals 1. So what's x? 0. Good. Okay. All right. So we got that. Now let's look what happens if you go to part C. Okay. We're going to approach this the same way. We would say log base 10 of 0 equals x. So if you write that as 10 to the x equals 0, well, you're going to run into a problem. Okay. It can't be 0 because 10 to the 0 is 1. In fact, it turns out this way. If you take any number and raise it to any power, you will never, ever, ever get 0. It's mathematically impossible, okay? So that one is undefined because you can't take 10 to a power and get 0. All right, I'll explain that a little bit more thoroughly here in just a second here, all right? Let's look at this next one. Let's see why you can't do a log of a negative number. Well, you would write this as log base 10, -1 equals x. So you'd write that as 10 to the x equals -1. Same thing happens. If you take 10 to a power, you will never, ever, ever get -1. It's mathematically impossible. Okay? So let me kind of show you a little bit more thoroughly why that is. All right? So here's kind of the idea. Now I'm doing this backwards with exponential. 10 to the second's 100, but 10 to the -1 is 1 over 10, which is a positive number. Okay, if you take 10 to a negative power, you're going to get a positive answer. Okay, if I take 10 to the 0, I get 1, so it's always positive. The idea is if you take 10 to any power, it will always be a positive number. Does that make sense to you? Okay, that's what you need to understand is 10 to any power is positive. There's no power of 10 that will ever be negative or 0. Can't be done. Okay, so that's why you can't do a log of 0 or can't do a log of a negative number. Okay, so now we transition into domain. So when we look at domain of a log function, what we look at is the argument must be positive. That's how you figure out the domain of a logarithmic function. And that's going to tell you what x can be. Okay, so on this, when I'm talking about the argument of log base 3x minus 4, I'm talking about what you're taking the log of. So what you want to do to figure out the domain is you take that argument and you set it greater than 0, because it has to be greater than 0. Now, that's a super easy inequality to solve. We've learned how to solve inequalities. You add 4 to both sides, you get x is greater than 0. 0 plus 4 is 4. Okay, so we would get that. That's your domain right there. So set builder notation, we've learned how to do that. You would say set of x such that x is greater than 4. So x has to be greater than 4 on this problem. Now, how would that be in interval notation? Where to where? If it's greater than 4, how do you write it in interval notation? 4 to infinity, right. So you would have parenthesis 4, comma, infinity like that. Okay, so that's how that goes. And see, the idea, this is what would happen. If x is equal to 4, you would have log base 3, 4 minus 4. You would have log of 0, and log of 0 is undefined. But once you're past 4, you would be able to get an answer. Okay, that's the idea. Anything past 4 guarantees you're doing a log of a positive number. That's the idea. Okay, so all these problems are going to be done the same way. If you're asked to find a domain of a logarithmic function, you look at the argument. It doesn't matter what the base is. You just take on this part B on the next page, you would do 2 minus x greater than 0. Then you would have to solve that inequality. Okay? Now, if I solve this inequality, I'm going to do it this way. I'm going to subtract 2 from both sides. That will give negative x greater than negative 2. What do I got to do now? Divide by negative 1, right? What do you do with an inequality if you divide by a negative? You remember that? Switch the sign. Good. Okay, so that would give you x is greater than, or I'm sorry, x is less than positive 2. Okay, so you have to remember some of the things we learned about inequalities. So set builder notation, we'd say set of x such that x is less than 2. Okay, and how would that go in interval notation? Where to where? Negative infinity to 2. Good. And make sure you have a parenthesis on the 2 like that. Okay, so that's how that would get put together. Okay. All right. Next problem, same thing. It's going to be the same thing over and over again. You have to know that regardless of the base of the logarithm, you just take that argument, you set that greater than 0, you solve the inequality. This one you could add 5 to both sides. You'll get 4x is greater than 5. Then you divide by 4. If you divide by a positive number, do you have to switch the symbol? No. Okay, so you just get x is greater than 5 over 4. So your domain, you would say set of x such that x is greater than 5/4. Okay, so that's it. Interval notation would just be parenthesis 5/4 to infinity like that. So if you're asked to find a domain of a log function, you just have to understand that the argument has to be positive. So that's why you set it greater than 0 to solve. Okay, any questions? Okay, so you have to understand you can only do a log of a positive number. If you understand that and understand why, then it's easy to figure out what the domain is. Okay, all right, go ahead and do the 3 problems below. Kind of do the same thing, write it both in set builder notation and interval notation. No problem. Okay, there's nothing to it. All right, so it's just solving inequalities. So I think everybody got those okay. I didn't look at the number 3 with everybody, but solved the inequality. The only one you had to switch the sign on was number 2 because you did divide by negative 3 on that then. Okay. Now I have a problem on number 2. I didn't write my answer right. I don't know why I put a brace there. That should be a parenthesis there. Okay. All right. Any question about that? Okay, so the idea is a logarithm can only be a log of a positive number. That's how you figure out domain. All right, now the other part of the section we're going to look at is graphing. And graphing a logarithmic function without a calculator, you have to kind of be careful about what values you choose for x. And what I'm doing on this example 3 on the next page is we're going to construct a graph of log base 2 of x. Now, I didn't just pick any number. I picked 0. I didn't pick any negative numbers because you know you can't do a log of a negative number. But we also learned that log of 0 is undefined. So I want to go ahead and start at 0. You want to just label that that's undefined. You can't do log base 2 of 0. But what I did is I picked numbers where you can get numeric answers in your head. Okay, so let's go through and just kind of work these things out. And you'll see a pattern on this. So we need to do log base 2 of 1. And you'll get to a point where you can start doing these in your head. If you set that equal to x, really what this is saying is 2 to what power is equal to 1. So what power do you raise 2 to get 1? 0. Okay, good. We don't have to set these equal to x. You can start thinking of it more this way. So if you go to the next one, you're really thinking of log base 2 of 2. You're asking the question, 2 to what power is 2? So what's that? 1. 2 to the first is 2. That's it. You're going to see a nice pattern on these problems. Go to the next one. That's really 4. 2 to the second is 4. So if we do log base 2 of 4, what does that mean? 2 to what power is 4? So what's that? 2. You see a pattern? 0, 1. See, I picked numbers this way on purpose. The next one, 2 to the third is 8. So we have log base 2 of 8. That's really 2 to what power is 8? So that's 3. Okay. And then the next one would be 4. That's 16. So 2 to the fourth is that. Now, I want to show you a pattern that exists on this. You don't need to write this down, but if you do the log base 2 of 2 to the 0, the log base 2 of 2 to the first, log base 2 of 2 to the second, and so forth, notice the answer was the power, okay, automatically. So what do you think would happen if you did log base 2 of 2 to the 100th? Do you know what the answer would probably be? 100, exactly. That's what I'm trying to show you, is that exponent, that power of 2, is what that logarithm is, okay? So that's kind of a nice thing to begin to see. Okay, so let's go ahead and let's just graph this. So go ahead and label your x-axis. Just go out to 16. That's the biggest value. We have 8. We have 4. So you can just kind of put that together like that. And really all we need to go on the y-axis is up to 4. And then we're just going to plot these points and kind of talk about what this graph basically looks like then. So what you want to do is go ahead and just plot your points. 1, 0, just kind of estimate where 1, 0 is. You've got 2, 1, estimate where 2, 1 is. You've got, 4, 2 was a point. We had 8, 3 was a point. And then we had 16, 4 was a point like that. So I'm just plotting the points like that. And then your graph is going to go like this. If you connect these dots, it kind of goes through that. What's going to happen is the graph's going to level off, but it's never going to go completely flat. It's always going to increase forever. And then the y-axis acts as a vertical asymptote. So you want to make that graph go down towards the y-axis. So it looks like that. That's what the graph of a logarithmic function looks like. It's like that. Okay. Now, as far as information on this, what do you think the domain is just by looking at the graph we just drew? Remember, domain's what x can be. So what does it look like x can be in this problem? What did I say? What kind of number can you take a log of? There's only one kind of number you can take a log of. positive, right? So that means that the domain is 0 to infinity, right? Now the range is y. What does it look like the graph does? It looks like the graph goes down forever, and it looks like it goes up forever. So what's the range? Negative infinity to infinity. Good. Okay, so we got that. Okay, all right, and that's what the range is always going to be on a logarithmic function. Okay, do you have an x-intercept? Did we cross the x-axis? Yeah, where did we cross? 1, 0. Okay, so the x-intercept's 1, 0. That's going to show up a lot on here. Did the graph ever cross the y-axis? No, so we do not have a y-intercept, okay? Vertical asymptote, we have one. Remember, a vertical line is x equals something. X equals 0 is the vertical asymptote. So the reason you don't have a graph to the left is because you can't do a log of a negative number. So you're only going to have a graph with positive x values like that. So that's how you do that then, okay? All right, so if you were doing log base 3, you wouldn't want to just choose any number. You would want to use like 3 to the 0, 3 to the first, 3 to the second, 3 to the third, and so forth. You want to use smart numbers when you make out your table, see, okay? All right, let's do this next one. And I did a few more different numbers on this. First of all, you know that log x really is y equals log base 10 of x. Okay, so we're going to do all this same stuff again. If we do the log of 0, we know that's undefined, so you can't do that. And let's just reason as many of these out in our head as I can. So now we're going to do log base 10 of 1. That means 10 to what power is 1? So what 10 to what power is 1? 0. So you get a 0.10. Okay. The next one's a little harder. It says, this is saying log base 10 of 2. So what this means is what power of 10 is 2? I have no idea. 10 to what power is 2? I don't have a clue. So let's take our calculator and find out. And since this is an log of base 10, your calculator will do that for you. So if you type in log of 2, you're going to get decimals. If you can't do something in your head, then your calculator is about your only hope that you have. So we'll just write that as 0.3. Same thing will happen on the next one. If you do log base 10 of 5, that's really saying 10 to what power is 5? I haven't a clue. Okay, so if I do log of 5, that'll give me some decimals. Let's write that one as about, let's just round that to about 0.7. Okay, now the other two you can do in your head. So what would be log base 10 of 10? That'd be 1, right, because 10 to the first is equal to 10. So that would be 1. How about log base 10 of 100? You can also do that in your head. That'd be 2, okay, because 10 to the second is 100. Okay, like that. Okay, so I just threw a couple other numbers in there to show you that, you know, if it's not something you can do in your head, then you're just probably going to get decimals. So just take your x-axis out to 10. Don't go out to 100. Just do kind of like this. And then 1, 2, 3, 4, kind of like that. And let's just kind of go up to 1 and down to -1 like this. And then we'll just kind of estimate how these go. I'm going to also do like 0.5, -0.5 like that, just so that we get a fairly nice graph on this when we do that. So not go out to 100, just go out to 10. Okay, if we plot the points, we would have a 0.10. So that's your x-intercept. You have a 0.2, 0.3, so just estimate it. You have a 0.5, 0.7, estimate that. And then you have a 0.101. So the graph is going to have the same shape as the previous example did. It will look something kind of like that. And then it will not touch the y-axis. It will just approach the y-axis like that. Okay? So the domain is It's got to be a positive number. Your domain is 0 to infinity because you can only do a base 10 log of a positive number. That's going to be the same. The range is all real numbers. The graph goes down forever and it increases forever. So y can basically be anything. Your x-intercept, again, is 1, 0. That's the point where it crossed the y-axis. That's your x-intercept. You don't have a y-intercept. Okay, it's never going to cross. If it's just a log with no transformation, it's not going to touch that. And then the vertical asymptote, just like the last problem, is x equals 0. Okay, so that's how a graph of a log goes. That's how you can kind of begin to wrap your head around why these graphs look the way they do. Any question on that? Okay. All right, now I'm going to probably just have you do one. I'm having you do a base 4 on this. So I want you to just go to the next page and see if you can put this one together. And again, I've given you good numbers on here. I've given like 0, 1, 4, and 16. There's a reason why I chose those numbers. As you're doing this, hopefully you'll understand why I chose the numbers I did. I'm choosing. All right, so we got, the log base 4 of 1 was 0. Log base 4 of 4 was 1. Log base 4 of 16 was 2. And I saw everybody kind of reasoned out that the next one would be 64 because 4 to the third is 64. 4 to the fourth would be 256. So you would just kind of get these numbers like that if you went out further. So when I graphed this, the graph has the same structure. Make sure that you're approaching but not touching your y-axis. Your domain's always the same. You can only take a log of a positive number. The range will be anything because the graph's going to go down and up forever. You do have the same x-intercept. See, we got that on every problem we did. And then we have that vertical asymptote. Okay? All right, very good. Any questions on that? Okay, so here's the next one I would do. Let's just do this one together. This one is natural logarithm. So what I did on this is I did the same thing. You know this is log base e of x. So I went ahead and just picked powers of e. And I went ahead and just took my calculator, and we learned that e is about 2.7183. E to the second, if you do it on the calculator, you get about 7.4 and so forth. Now, you want to learn how to do this quickly in your head because there's a trick. We know that we can't take a log of 0. But if you do log base e of 1, that's 0, again, because e to the 0 is equal to 1. The next one, if you're doing log base e of e, that's equal to 1 because e to the first is equal to e. Okay, then the rest of them go like this. If you do the log base e of e to the second, what do you think the answer is? I'm trying to show you a pattern. 2, exactly. How about the next one? Log base e of e to the third. What is that? 3. See how this keeps going? If you pick powers of the base, then it's automatic. And then the log base e of e to the fourth would be 4, like that. Okay? And again, so let's just take this out. Take your graph out to, only take it out to like about 7.3. Just take it out to 8. We don't have to go all the way out to 54, just kind of to get the idea here. You're going to see that the graph essentially has the same structure the other graphs we've done are. So I'm just going to take the x and y axis. I'm going to make y go from -2 to 2 like that. And then I'm going to plot points. You'll have this exact same kind of looking graph. So 1, 0, there it is again. It's the same x-intercept. Now, E is about 2.7, so you want to go over about 2.7 and up 1. Just estimate that point. Now, what I would like you to do on your graph is label that point as E1 and label the other point as 1, 0. Just label it like that, okay? And then the next point would be about 7.3 and then up 2. label that point as e to the second 2, and then just sketch in the graph like we've been doing. Okay, so it kind of goes like that. Again, it doesn't touch the y-axis, it just approaches that. Okay, everything else will be identical. The domain is 0 to infinity. You can only take a log of a positive number. The range is negative infinity to infinity. X-intercept is once again 1, 0. There is no y-intercept. And again, x equals 0 is the vertical asymptote. So the idea is no matter what the base is, the graph is going to look the same. Okay, it's going to have that same structure. It's going to have the same intercepts and everything is going to be the same. Okay? All right. Any questions on that? Okay. All right. Now, the only other thing I want to do in here is some transformations and just show you what you can do on your calculator to enter other bases. Okay. So let me just kind of get your calculator out, and this should be in the same location for everything. So let's say, for instance, that you wanted to put in your calculator log base 2 of 10. So here's how you do this. What you do is follow these keys. All you do is press the math button, and then you have to go all the way down, scroll down the list, and the way it is on an 84 is you'll say log base parenthesis. Now, if you got an 83, I don't know. Does anybody have an 83? Is it there? I don't know if it is on an 83 or not. I mean, there's a way that you can do that I'll show you, but I don't know if it's on an 83. 84, you have an 84? You have an 84? You have something on your phone, or is that? Okay, all right. So this is where it should be on an 84. So you just press enter. And if you press enter, then you can put in your base, and then you can put in the 10. I'll show you a little trick if it's not on there that I won't really be able to explain what it is until probably after fall break. But that's how you put that in. Okay, here's one more example. If you did log base 20 of 1, okay. I mean, I would hope that you know what the log base 20 of 1 is. Do you? 0, good. Yeah, okay. But here's how you would put it in. You would go math all the way down to the bottom. You would put your base in. And by the way, the log of 1 is, crap, what did I just do? Okay, there we go. So I put that in like that. Yeah, that's 0. Okay, so that's how you put it in. Let's see. So if you don't have this, here's how you can put this in. You could put ln of 10 divided by ln of 2. The other one, you could put ln of 1 over ln of 20. Don't worry about y. That's something called the change of base formula, which I'll show you after fall breaks over. So if you don't have that button, you could go for log base 2 of 10, you could just go ln of 10, close the parentheses, divided by ln of 2. On more old-fashioned calculators, that's just the way you typed in a log anyway. So did yours have that in the back, Christian, or no? So you do have it. Okay, good. All right. Do you have yours, Ernesto? Did yours have the button? Okay. I think 83s, I don't know. Older calculators wouldn't have that button. Okay, so what we want to kind of do on this problem example 6 is we want to use our calculator to figure this out. What I'm doing on these problems is we're looking at different bases. This is the graph of log base 2 of x. The next one is really the graph of log base e of x. And remember, e is about 2.7. Log of x is really log base 10 of x, then 15. So what I'm doing is the bases are getting bigger. Base 2, base 2.7, base 10, base 15. And notice on my graphs that they're getting bigger, okay? As the base is changing, the graphs, the y values are increasing. So let's just kind of see which is which on here on our graphing calculator, okay? All right, so I want you to just see if you can do this okay on your calculator. Go to Y1 and put in log base 2 of x the way I just showed you. So if you go to y1, then just put math, go all the way down till you find the log base button, and then put base 2 of x, like that. Okay, now we're going to put these in order. Go to y2, and now just put in ln of x. So you got an ln button, so you can use that. Go to y3, put in log, which is base 10. You have a log button, so you can just put that in like that. And then finally, if you go to log 4, put in the base 15. So I just want you to sort of see what happens as the bases get bigger. So with this one, you would have to go math. You'd have to go down to that option A, log base, and then I'll put in 15 of x like that. And then just do a standard window on this, or actually do your window like my graph is. Just make y minimum 0, make y max 10, and then make y minimum -5 and y maximum 5. So one thing you need to label on the graph that I gave you, just label your x-axis and your y-axis like this. Okay, now we put these in order, so we're just trying to see which is which on here basically then. So the way it works out is the first graph that came out on here, you have to kind of look at how this goes on here. So if I put this here, we want to see the first thing that should come out is log base 2 of x. Okay, so look what happens. So that's log base 2, that's log base e, log base 10, log base 15. So what you want to do is label this like this. This one is log base 2. The next one was ln of 2. Then it was log. Then it was log base 15 like that. Okay, that's the order. The way that on a graphing calculator, the top one is going to graph first. So it's going like that. All right, so what's happening on this? Basically, the bigger the base is, the slower it increases like that. Okay, so that's how that goes. So basically, what I want you to notice on this is the smaller the base, bigger y values, like that. Okay, so that's how that goes. All right, and if you put like one more in, if you did like, if you put like in y5, if you went with a bigger base, you wouldn't hardly even be able to tell the difference. If I did something like log base 50 of x, like this, and then if I graph that, well, it's just a little lower. So that's what you're going to see. The bigger the base, the lower the graph goes. All right. Okay, so next thing I want to talk about is transformations of log functions and kind of how these things go. So transformations work always the same way. The way that I like to teach this is if you're inside the log, then it causes changes in x. Okay, so the argument on this example would be the c parentheses x plus or minus d. Okay, so that's what you got there. So d is going to be left or right, and then c is going to be horizontal shrink by the reciprocal or horizontal stretch by the reciprocal. Okay, if the coefficient of x is negative, you reflect over y. Okay, that's exactly the way exponential functions work, and all functions work that way. If you're outside the function, then you're going to either be going up or down, or you will vertically stretch or shrink, or you will reflect over the y-axis. Okay, so again, when you learn transformations, always think of inside and outside. Inside the logarithm is left, right, horizontal stretch, shrink stuff. Outside is up, down, vertical stretch, shrink like that. It's always the same. That's why I like to teach it inside the function and outside the function. Okay, so if you go to the next page, this is kind of what I want to what I want to show you here to kind of organize this. Okay, so the first column, all of these numbers are outside the function. I'm going to highlight the transformation on this, and everything that I'm highlighting is outside of that function. Okay, so let's see if we kind of know this. So the first one is log base 2 plus x. I think it's better to put the 10 in front of the log. So what does that 10 do? What do you think? What? Up 10, exactly, that's up 10. That's outside. Remember, outside adding is taking you up. Okay, how about the next one, negative 5? That's the same as subtracting 5. So what's that going to do? There you go, down 5. Okay, all right. Okay, now the next one, what this does is it makes the y become opposite. Okay, so what does that do? Okay, be careful about the axis. It does reflect, but it reflects over x. And here's the reason why. What will happen is when you have that negative outside, it's just 5 becomes negative 5. So like the y value changes. If y changes from positive and negative, it flips over x, right? Okay, so that's the idea there. Okay, the next one, what this does is this multiplies y by 2. Y gets bigger if you multiply it by 2. So does that stretch or shrink the graph vertically? Stretch, that's a vertical stretch. Okay, so we will say that is a vertical stretch by 2. Okay, remember, if you're outside the function, everything is kind of logical to you, I think. The next 1.5, that would be a vertical shrink. The reason it's a vertical shrink is because y gets smaller. You're actually multiplying y by 0.5. So that is a vertical shrink by 0.5. The better you understand this, the more likely you are to remember this. Okay, if you understand how the number changes y, then it's easy to remember. Okay, that's how I remember all this stuff. Okay, so now we're looking inside the logarithm. Okay, every transformation in this box is inside of the argument. So that means now we're affecting x values. So this is where we get into left, right, horizontal stretch, shrink, and then reflecting over the y-axis. This is all the same that you've learned for every other function. What do you think the x minus 4 does? That's right, 4. Okay, remember, everything's backwards now. X minus 4, it seems like it would be left, but no, it's right. How about the next one, the plus 7? What does that do? Left 7. There you go. Okay, what happens is x changes. Okay, the next one is a reflection, but it's the opposite axis. Anytime you reflect, it's over the opposite axis. So this is going to reflect over y. Okay, now here's where it's weird. You get into horizontal stretch shrink. So since it's inside, you're going to say horizontal, but the reciprocal, okay, the reciprocal of 2 is 1/2. So that will be a horizontal shrink by the reciprocal. Okay, if you remember reciprocal, that'll help you understand whether it's a shrink or stretch. Okay, the next one is a horizontal stretch by the reciprocal, so by 3/1. Okay, see, everything's totally backwards when you're inside of a function. That's how I remember it. Right, left, and then the horizontal stretch shrink are always by the reciprocal. We learned that a lot more specifically earlier in the semester. Okay. Okay, so what I want you all to do for a minute here is I've given you 5 graphs. Okay, and the one that's in, I don't know, you can't see colors on here real well, but let me kind of just highlight this for you guys so you can understand this a little bit better. The one that's in blue is the one that's not the transformation. Okay, so I'm just going to kind of highlight over the original function. I did these all on my graphing calculator. So the graph of what I just highlighted is log base 2x. Okay, so what I want you to do is match the function with the graph. And every one of these things have one transformation. Maybe they're up, maybe they're down. I think all these things are outside the function. So it's all up, down, reflect, stretch, or shrink. Every single number on here is outside the function. So I'll just give you a minute to see if you can figure those out. And then I want you to do the same thing on the next page. Everything is inside the function on the next page. So you're going to be looking at horizontal, left, right, stretch, shrink, stuff like that. Okay, and again, the given graph is the one that's in blue. I know that's hard for you all to see. So it's the graph like that, okay? Okay, so I'll give you a few minutes to do that, then we'll kind of finish up with one problem here. You can just put the letter by the graph if you want to. That's the way I did this. I just did that. And then do the one on the next page here too, okay? So it's just a matter of knowing up, down, stretch, shrink, reflect. Those are the key things that I'm trying to look at to see if you can do okay. So that one is right 4. That looks good. That one's left 2. That looks good. The reflection's the easiest one to see. Okay, and then the stretch shrink, okay? We'll see here in just a minute. Okay, let's see just on this page. That one will be right 4. So what did you put on that one now? Okay, that looks good. That one's left 2. That seems good. The reflect's easy to see. We'll look at stretch shrink here in just a minute. Okay.
I wasn't sure which one was the original one.
The original one is, let me just kind of display that. So that's kind of, can you see kind of where the original is? It's the one that I've highlighted. So that might help you a little bit on that. And let me kind of, while you're working on this, let me see kind of what it's all on here. You got it figured out, or you're still working on it? Okay. I just want to look kind of what you have on the other page. The easiest one to see is always the reflect. Up down's pretty easy to see too. Stretch shrink's always a little bit harder. All right, well, let's see if we got these right. And then I'll finish with this last example here. Okay, so if you'll go to that first page, just see if you got this figured out. So this is the way this one was up 3, So this one was that graph. A is this one. This one was down 3, so B was this graph. This one was reflect over X. That one was C. And then this one is a vertical stretch by 2. And then E was a vertical shrink. So the way you can tell the difference between those two is D would be bigger. It would be above the graph. And then on E, that would be below the graph like that. Okay, did we get that, or is there any of them we didn't get? We good? Okay, all right. Next page would go like this. Let's see if we got these figured out. I think these sometimes the stretch and shrink are harder if they're horizontal. Okay, so this is kind of what I got on this. So the first one, A, was right 4, so that matches. That one's pretty easy to see. Then you had left 2, so that one was this one. That one's easy to see. This one is reflect over Y. I think that one's easy to see. And then remember, when you're inside, it's the reciprocal that makes the difference. So this one would be a horizontal shrink by 1/3. So that one matches this one. Okay. And then this one right here would be a horizontal stretch by 3/1. So that would end up being, hold on, I think I got those backwards. I may have got those backwards. Okay, so it goes like this. If you're shrinking horizontally, it would be kind of like this. So if you look at D and E, it goes like this. The blue graph, this one is being stretched. This one is a horizontal stretch because you're pulling on the graph this way horizontally. This one right here is the shrink, like that. So I do have those backwards. Okay, so D would be the shrink, and then that one would be the stretch. Okay, do you understand that? Because if you're horizontal, you got to think of it this way. This one right here, you're pushing on that, so you're shrinking it. Versus this one right here, you're stretching that. You're not doing the stretch shrink this way, you're doing it this way. Kind of like an accordion is kind of the way I think of that, like that. Okay, that's a little tricky to do that. So I wouldn't be surprised if maybe you got those backwards like I did. I screwed that up when I was working that out while you were working them out. Okay, so let's do this real quick on your calculator. This is the last thing I want to show you. We're going to solve an equation. You'll see one of these on web work. So you want to go to your calculator, and we're going to solve this equation with the calculator. Okay, so here's what you want to do. You want to put in Y1, put in the left side of the equation. Okay, so the left side of this equation is log 5x plus 2 minus 1. Then you want to put the right side of the equation in Y2. So that is 1 minus log 5x plus 2. You have to do this equation on your calculator. Okay, so let me just take you through how you do this with your calculator. So go ahead and get these put in. You got log 5x plus 2, and then minus 1. That goes in Y1. That's the left side of your equation. Right side of the equation, put 1 minus log 5x plus 2. Okay, now I'll give you a window to do on this. I went ahead and just gave you the graph on this. Just do, make your x go -5 to 5. Make your y's also go -5 to 5. You have to kind of figure out a window so you can see where these things intersect. Okay, so just get your window set up, go -5 to 5 by a scale of 1 on x. Do the same thing for y, do -5 to 5 like that. And once you've got those two things in and then got your window set up, you should see the same graph that I gave you. That kind of looks like that. So what you're doing on this to solve this equation is you're looking for this intersection point, and you just need to do the keystrokes that I gave you right here. Okay, so get your graph put in and then do exactly what I've got these keystrokes here. Go second trace, go down to option 5, and then press enter. what it's going to do is it's going to say first curve, and it should be blinking on one of the curves. If that cursor is blinking on the curve, press enter. Then another cursor will come up on the other one. If it isn't, you have to kind of move your cursor, press enter again. Then it will say guess, press enter again, and then it will give you that intersection point. So that intersection point is 1.60. So that means the solution is x equals 1.6. So what you're doing is, I noticed in web work there was one problem like this. It was just trying to teach a student how you can use your calculator to solve an equation. So what you do is put the left side in and graph it, put the right side in and graph it, and try to find where they intersect. Okay? So if you can get everything put in there correctly, then it should work fine on there. Okay? Did you guys try that to see if it worked? Did it work? Okay? All right. The only thing that can happen sometimes on these is you have to figure out a window. When you look at your graphs, you just got to see that you have to be able to visually tell where they intersect. And if they do, just follow that intersection command on the calculator. And whatever x is of your intersection point, that's the answer. Okay? All right. Well, that'll wrap us up then. So glad last. 3 out of 15. Okay, we got a lot of things done. You guys did great. All right, just get that homework done. Have a great fall break. And when we get back, we'll just have a couple more sections to finish up. And then we'll be talking about the final and be doing review and that kind of thing like that. I just marked everybody off. You don't have to sign it. There are only 3 people, so I got it all figured out. Okay.